the when the solo parts weren't going on. What, Jasper's too busy? He's too good to listen to us. He's got to have his earphones on. He's such a snob.
Sorry, I have one too.
We were just talking about why Charles isn't on the step team.
Yeah, I'm really puzzled by that too.
I would pay so much money to watch that one.
Mr. Spraggins, I applied, but they wouldn't let me in.
Oh my god.
Oh yeah.
You auditioned.
I auditioned, yeah.
I applied.
I had this idea that for our next faculty, fun assembly, all of us should get jobs. We should have a day where all of us have jobs that are totally inappropriate. Like Miss Hall, director of musical.
Oh, that kind of.
Oh, that's good. I like that.
Me being like football coach. Okay, it's rehearsal time.
Why is there not a secret?
I know.
I don't know, Eric.
Let me see a little bit of this.
Yeah, I feel a little cut out. Who am I?
There you are. Hi, Logan.
I'm Julius.
2x2x30. This two.
I was waiting for you.
So guess what? I was in there for a while trying to scare somebody,
Oh my god.
and I had like my phone out and everything,
That's
and then
actually
like
step.
the tech dude walked by, and I felt really embarrassed, so I just left.
I think that's so funny.
He got
The
me.
tech dude. I like that.
I really don't know his name. That was not nice of me, but I really
Mr.
don't know his name.
Wade. Mr. Wade.
I would have asked, but I was kind of embarrassed.
Yes, like Wade in water. So
I was
if
also
you're
afraid that I was
wondering-
going to scare Mr. Spraggins and then he'd get mad at me.
I don't scare easily, I have to admit. Like when I go to haunted houses, I'm like, this is so dumb.
The Haunted Forest sucks. I wish it was scarier.
What? No, it's terrifying.
I'm trying to like grab you.
But it's not real.
That doesn't mean it's not scary.
It's startling.
You don't know that?
It's not scary because you know how unreal it is.
Somebody could
Yes.
totally like pretend to be Cards to staff and just bring a chainsaw and just attack you.
Someone could do that on any day.
Yeah, but you would
Actually, I have a
it would be
chainsaw in my
normal within the
office right
context
now.
of the haunted forest, and that's scary.
Well, aren't you running anyway?
Alex, how? How's
Not fast
it going?
enough.
Hold on, I'm trying to figure
How
out how
you
to
doing?
That's the actual fear you're having when you're there. You probably shouldn't go.
That is an actual fear.
Alex got a haircut. Alex probably got a haircut.
Who put the Julius? What's your name?
What?
And hello, Trinity Prep. Oh, wow. We're doing good. Okay. So in case you were wondering if you wanted some, here's some advice for you, but remember that I don't come cheap, right? It needs to be like in the $1,000 range, at least.
Wait, what?
See the cartoon. Is there anything I can do for extra credit, like give you money? So, anyway, the answer is yes, of course. So, yesterday, for those who are not at Murray, we had a talent show, and there were a number of pretty good jokes told at the talent show.
I agree.
Logan, would you like to tell one?
Oh my god.
Yes. What do you call That's hilarious.
What do you call someone who skips church?
Christian. Wait, what?
Okay, you did it wrong.
Wait.
Okay. It's,
God.
what do you call it when Batman skips church?
What did he say when who?
Batman
No, what-
skips church.
What did Logan say? I got one.
Christian Bale. Okay, forget it. Yes, Julius.
Okay, what do you call it when there's a pepper in your face?
Okay, you're doing it wrong.
Yeah.
All of you
No,
are
I'm not.
doing it
I'll offend your
wrong.
business.
How do you find Will Smith in the snow? You follow the Fresh Prince.
That was okay.
So good.
Actually, my favorite one was the jalapeno face.
No, jalapeno.
The jalapeno business was easily the best joke ever told.
Yes, it really was. Okay, so by the way, if you truly want to, maybe on the exam, one of the questions should be right here your favorite joke
No, me.
in the English language.
Make it worth a lot.
My favorite math joke is about like, what did the Little Mermaid wear to math class? Her algebra.
Oh,
What did you say?
What did the Little Mermaid wear to the math
I heard that too.
algebra?
Oh.
Isabel is having problems. Okay, here we are.
These
Let
mildly
us do
entertaining.
this problem here to get started and to settle down. I'm in such a festive mood today. Here we have chain rule practice, one application. Okay, yes. So this is like if you have x is a function of r, x is a, what is it called? Polar coordinates. Help me out. So let's concentrate on 1 and 3 and bonus question number 2. So see if you can do these 1 and 3. And if you're super, do number 2.
If I'm super. I don't know.
If you're super.
Whoa.
I thought that was open. I was
If
like,
you're not super, then.
Then leave the class.
Oh, look, there's a joke right there.
1 point for Isabel.
So, Max, are you disappointing me by not being able to do number 2?
No.
Okay. I'm judging you
Pi
already.
over 4.
What?
Is the cosine of pi over 4 root 2 over 2?
You don't know what the cosine of pi over 4 is? What?
I think it's. I know what I think it is.
Lame.
Is it root 2 over 2?
Or 1 over root 2. Same thing. Root 2 over 2.
But you don't
That is actually disappointing to me, Charles.
Well, I got it in the end, didn't I?
You got it in the end, but you had to.
Got it in the start.
Theta is a variable. It's
Uh huh.
not. Okay.
It is a
I'm
variable.
just making sure.
Yeah,
that
that's
it
a
could be a
variable.
constant.
I don't even know what to say. X, dr. Silence is eerie.
Mr. Magnus, do you want us to raise our hand when we've done one and three, or do you want us to do two as well, or what do you want?
What do I want? That is a really deep question, Jasper. Yeah, let me. I'm actually going to stop this pretty soon. So I'm going to ask Julius to help me get started because I have no idea where to start, Julius. Oh my God! Oh my God, you guys! Julius, tell me how to start. I'm so confused.
Yeah, so am I.
Awesome. Okay, Akshay.
Okay. That works.
Can you help me? Because Julius was a total failure. So.
For number one, how to do it?
Yeah, just tell me what to do.
Well, dw over dr is dw over dx. I mean del w over del x.
I gotcha.
Times del x over del r plus del w over del y times del y over del r.
Woo!
Oh, wait.
Rock and roll. Okay, I think probably what I would have said, the only thing I might have said differently was del w del x dx dr plus del w del y dy dr.
That's all you don't want us to compute it.
What was that?
You don't want us to compute it?
Yeah, I want us to compute it. My goodness, we just have to start somewhere, Logan. Gee, you're mean. Okay, Raheem, can you help me?
Project this somehow?
It's there.
Yeah.
Yes, you go.
On what?
Raheem, oh my gosh, you're wearing a tie. What's going on? Why are you wearing a tie? Why are you all wearing a tie? Oh my goodness. So what happens? Do you, I don't know. Is there like a donkey and there's a crash and...
We sing a lot too.
Yeah.
It's a lot of fun.
Okay, good. And how long does it last? Like 7 hours?
That's what it feels like.
Like an hour and 20 minutes.
Yeah.
We have one of those on Friday. You know what's funny about it? There will be like probably no Christmas songs sung in it. Ours is so secular. It's like kind of. I mean, are there any? Are you in the choir this year? Yeah. There's like virtually no Christmas music in it. So okay. Anyway, go ahead, Raheem. Help me out with part of it, or all of it.
Okay. So first you want to get d or del w del x. So
Cool.
Well, actually, what I did first, I saw on the w function that it was a product, so I just multiplied it out to make it easier for the partial.
Cool. That works for me.
And then I got for del w del x 3x squared y plus y cubed, and for del w del y x cubed plus 3y squared x.
Fantastic. Okay, and then for del dx dr, you get.
I got negative r sine theta plus cosine theta.
So let's see. Del x dx dr is. So.
Should have just be
It doesn't need a product rule or.
You don't need the product rule because I've just got one. So I've got r.
Because we're taking it in the derivative of r, right? In terms of r. So then it'd just be cosine theta?
It'd be cosine theta, that's right. And then dy dr would be sine theta.
So, okay.
Okay? And then Max, what do you do after you multiply that stuff together?
So then you can get something really long, but I would suggest putting r cosine theta and r sine theta back into where you have x and y.
Right. So you have to eventually get it all
before you evaluate.
In some variable. And then you have just put in for r equals, you put in r equals 2 and theta equals pi over 4. Eventually for 3, right?
Right.
Okay, Julius, tell me what was confusing for you, my friend.
Well, because when I looked at the problem, my first thought was to just substitute in and then just like directly, and then
Why would that not work with this problem?
It doesn't not work, but that's not what it asks us to do.
Yeah, that's right. You could do it, but it says use the chain rule. So, that's not using the chain rule. Cheater, cheater, cheater. What is it? Cheater, cheater, pumpkin eater. There you go. Cheater, cheater, pumpkin eater. Okay. Did anyone remember
me.
the phrase the total differential and how to compute that? Anyone? No takers? So well.
I think I got it.
Thank you, Raheem.
Yeah.
You're bringing your A game today. You're wearing a tie, and you remember this.
Okay.
What would happen if you wore? What would happen if you didn't wear a tie to Christmas chapel?
Oh yeah.
They either send me home or make my mom bring clothes for me.
Really? Wow, I love it. Okay, go ahead, Raheem.
The total differential is dz equals del z over del x times dx plus del z over del y times dy.
Yeah. Okay, good. So, Charles, can you help me translate that into this problem?
So you take. And sorry, what was the formula again?
So, say it again, Raheem.
dz equals del z over dx times or del x times dx plus del z over del y times dy.
Okay.
Okay.
What?
So you have.
Go ahead.
Yeah, so you have del z over del y.
Or del W.
Or in this case, del w over del y, because we found it when we were doing part 1. And you have del w over del x. So you can just plug those in and.
Yeah. And you'll find what dw. So it'd be del w dx times dx plus del w dy dy. So you're actually going to have, it's going to have dx.
Wait, I'm confused.
Here.
Are those dells or d's?
Those are dells, and those are d's. Okay, I don't want to spend a lot of time on the total differential because I don't even ever use it ever, so I doubt that you ever will. But here we go. Oh, let's talk about, this is such a fantastic topic. Okay, this is actually one of the funnest things we talk about, I think. The figure shows a topographic map carried by a group of hikers. So imagine, I don't know, let's see Coleman and Samya out in the wilderness. And it says, sketch the path of steepest descent if the hikers, not stikers. Hikers start at point A, and if they start at point B. Okay, I'm going to ask Charles and Sam to draw here. Okay, Charles, I'm going to make you a presenter, and Sam, I'm going to make you a presenter, and then we're going to see what happens.
Wait, are you allowed to?
What?
Akshay asked if you're allowed to jump off the cliff.
I think that would probably be unwise, but if Samya were to push someone off a cliff...
It would be you.
I know.
Wait, where?
I can't control that. Okay, so Sam and Charles, you should have the... Oh, my gosh. Okay, so someone has drawn. So, Charles, are you going to do A? And
I'm doing B.
Okay, you're doing B. Sam, are you doing A?
Oh, I just did.
Okay.
Oh my gosh.
I know. Oh my gosh. Okay.
Was that
So.
straight, or did you mean to go to the?
Yeah, I think they should probably be straight-ish. They should probably be straight-ish lines.
Charles, why did you have the first one come up and around that area?
I don't think you did that.
I didn't do that one. I did the one that goes straight up.
Who did this one? Okay. Okay. So wait, I'm de-accessing your powers. Okay. So, Sam, talk about your drawing for A.
Well, the path is steepest when the lines are close together. And so I just tried to follow I guess, well, also another way to look at it is the shortest distance between two lines is going to be the steepest path.
Okay. So A, I think it's pretty clear that A would be, going off this way, as Sam has more or less drawn. It's a pretty squiggly line, but still, that is pretty much the line of steepest descent. Okay, what about you, Charles? Explain
the one I drew was the one with the arrow pointing at it, and I tried to draw the line so that it was always perpendicular to the contour lines.
Now, why did you do that?
Because in the video you mentioned that
there you go.
contour lines are always perpendicular to the directional
derivative. Right. Okay,
The gradient.
and so the gradient is this idea that we're going to talk about today, the gradient and what the gradient tells us. And one of the facts is that the gradient is always perpendicular to the contour lines. So when you're drawing a path of steepest descent, it should be perpendicular to each of those contour lines. Yes, Max, you had a question.
Well, I was going to say, I was talking with, I guess, a couple other people about the gradient and sort of saying how if you had like some function and you have a marble, you could sort of predict how it would roll down. But I was thinking about your example in the video with the ski slope, right? And even with like this example, the path of steepest descent, as say like Charles drew for us, it's not necessarily the path that will get you, or I'm wondering if it is the path that will get you to the bottom the fastest. Because the other, even if the other line that's drawn from B, even if for the first couple rings it doesn't go the steepest path,
but then it does for a while.
Yeah, but then it does.
Okay, so Isabel, you have a comment.
Well, I mean, I think that when you're trying to find like the steepest, then you need to account for like the total displacement, or not displacement, but the distance traveled of the person. So if they have to walk like really far along like a flat plateau to then get to an incredibly steep drop off, then you factor in the fact, like the amount of like steps taken or whatever per descent traveled, if that makes any sense.
Right. So like one of the issues with the other line in B that appeared is the person is actually on flat land a lot in B, in this one on the left. You see what I'm saying? In this one here, in this one
to the left.
This
all those
one.
big flat lines.
These, see, because here, like, you're on this flat plane. I mean, you're on flat land a lot.
Right. But even like that contour line, Charles's path hasn't even
Has some, but less, I think. I mean, and the main thing is that, I mean, like, this is, look at this here. Like, this thing is walking all along a contour line for a while.
Yeah, I don't think that was perfect. I'm not sure who drew that.
Like, you could think of it like if you had some like spot on a hill and you could go up over a little bump and then straight down a cliff to the bottom, or you could just go down a gentle slope all the way to the bottom. The path of steepest descent would be down the gentle slope, because you wouldn't want to go up and then down.
Right.
Even though that path might have a steeper average descent.
Right.
Really?
It's not the path of steepest descent.
So this is actually one of those things that's incredibly practicable in terms of surfaces. I mean, there's the kind of silly way of thinking about it with hiking or skiing, but also on a graph, like where the graph is changing most rapidly is of great interest to us. I mean, if you remember from calculus, that was a big, I mean, from single variable calculus, that was a big idea. Okay.
Computer science too.
Yeah, absolutely. So let's see. We have a function here, pretty function, 8y over 1 plus x squared plus y squared. So the first thing that says, analytically verify that the level curve at the level c equals 2 is a circle. Okay? Samya, what am I going to do this?
You can take the derivative, would you draw a contour?
So remind me what a level curve is. Anyone can tell me that. Alex Powell, can you tell me what Alex Powell is tying something around and he's doing a dance with his charger. Yeah, can you tell me what the contour lines are? The level curve, which is a contour.
What a level curve is?
Yeah.
It's like the circle that defines like the elevation at some level.
Right, I wish I had my picture. It's like you've got a mountain, and you're slicing that mountain at certain points, so you're setting the z equal to some constant value. So, Samya, does that help you think about A differently?
Yes.
So how does it make you think about it?
I'm not really sure how to.
Okay, that's okay. Jack, can you help her?
Um,
I'm about to cry.
you might start crying.
Okay, Logan, can you help me?
Bring out the tissue.
Oh my gosh, Coleman, save this terrible situation.
I'm not sure. There's no C in the equation.
Oh my gosh, okay. So what does the C represent, Coleman?
I'm guessing a constant.
It does, yes. So it says verify. So what happens when we do these level curves? We are setting the Z equal to a constant value. So I'm saying let's show that the level curve at C equals 2 is a circle. So does that help, Coleman?
Yes, I'm going to guess then C is f of x, y.
Yes. So what equation should I write?
2 is equal to 8y over 1 plus x squared plus y
I knew
squared.
we'd get there. I knew we'd get there. Do you see why I was about to cry, Logan?
Yeah, because that's embarrassing.
Yeah, that's pretty. Yeah. Okay, so let's see. I want to show that this is a circle. So Jasper, help me do that.
Well, so then you have C equals 8y over 1 plus x squared plus y squared. And then I think you can, then you multiply both sides by 1 plus x squared plus y squared. And then I think you can do, what's it called? The thing.
Oh my gosh.
Completing the square.
Completing the square, okay. Oh, the thing. Okay, so, gosh, Jasper, do you remember how to complete the square?
I think so. Wait, so we have C plus cx squared plus y squared minus 8y equals 0. So then with regards to 8y, it would be y minus 4 squared, right? Plus, and then minus 16. What?
Yeah, okay, so he's looking at the y terms. So he's collected the y terms, y squared minus 8y. You take half of the 8, you square it, you get 16. But since you added 16, you must subtract 16. Okay?
Subtract 16.
Yeah.
And then we
now the 2 is a little more difficult.
Oh, wait, since you added.
You have no linear term for the 2. What was that?
Since you added. What do you mean subtract 16?
Oh, well, remember in completing the square, part of the game is that you have to balance both sides of the equation.
Right.
So since you added 16 to make a perfect square out of y minus 4y,
you don't
must
just
subtract.
add 16 to the other side.
You could. That's another way to do it. It's just as long as you've accounted for it. What about the 2x squared, Jasper?
Well, I would. Well, wait, 2x squared? You mean cx squared?
Yeah, cx squared. You're doing it symbolically. He's trying to show off by doing it symbolically. What can I say?
Sorry.
It's okay.
Well, then we have to factor out the c. So then we do c times the quantity x squared plus 1. And then could you like x plus
y x squared
1
plus 1. I don't have any other x. I don't have any other x squared terms. X terms.
Well, I see. So it's just c times x squared, then it's just x squared minus 0, essentially squared. X minus 0, the quantity squared.
Make a mistake.
Shouldn't there be a 2 on the y?
Wait.
I made an error. And actually, I allowed Jasper to make an error because I made an error. Help me out, my friends. Can you help me over there in Trinity Prep?
Well, for the y, when you do y squared minus 4y, when you take out the 2, shouldn't it be plus 4?
Yeah, I made an error. So the thing I would do actually is I would write 1 plus x squared plus y squared equals 4y is the equation I would be working with.
Wait, so are we doing this without c?
Oh, okay. Yeah.
Substitute 2.
It's just asking me to show and c equals 2.
I see.
This is like an algebra 2 problem, and we're getting stuck. It really is an algebra 2 problem.
Well, at least it's not when we're trying to do the speed of a particle.
I know, it's so...
It's an entire class talking about it.
Right. So let's see. I have x squared plus y squared minus 4y plus 4. Okay.
Wait, where did you get the plus 4?
Well, I completed the square.
Okay. Oh, you completed the square.
So that's x squared plus quantity y minus 2 squared minus 3 equals 0. So that's x squared plus y minus 2 squared equals 3, which that is a circle, people.
Okay, I have 1.
This is going to be one of those days. I just sense it. Okay, so that is a circle. It is a circle of radius. What?
Is this what you got?
That is
Radius.
what I got, Isabel. You must feel so
Wait, I think
smart. Alex Johnson, what is that? That's a circle of radius what? Centered where?
I'm writing algebra.
Radius root 3 centered at 0, 2.
Radius 3.
Yes, and look, there's a picture of it right there. All that work for nothing. Okay, Alex, would you read the next? Alex Johnson, would you read the part B?
Sure. At the point root 3, 2 on the level curve for which c equals 2, sketch the vector showing the direction of the greatest rate of increase of the function.
Oh my gosh. Okay, so now it says sketch the vector showing the direction of the greatest rate of increase of the function. And then read C, Alex.
At the point root 3, 2 on the level curve, sketch the vector such that the directional derivative is 0.
Okay, so we need to make sure we know what the directional derivative is. So we got to talk about that next. So let's hold this problem. Let's move on for a second. Whoa. Okay, first we need to start with this thing called the gradient. Okay? The gradient is the way we notate it, and we will use this the rest of the year in this class. It's like an upside down triangle. And the gradient is actually super easy to compute. It's really, really easy to compute. Eric, do you remember how you compute the gradient?
I think you take the partial derivative with respect to x times cosine plus the partial derivative with respect to y times.
Oh, wait, just for the gradient, not the directional derivative.
Oh. Are those not?
Okay, so the gradient, right, is just, it's a ordered pair. Can someone else help?
Sorry.
Thank you, Julius.
Yes. Sorry. It's the partial derivative of x times the vector I plus the partial derivative of y times vector j.
Okay, so it's a vector, right? That is, the I component is the partial with respect to x, and the j component is with respect to y. Okay, so let's compute that. Julius, help me out. Let's see, for this one, I want to compute the gradient.
Okay, so the partial derivative with respect to x is 2x plus 2y minus y to the third. And the partial derivative with respect to...
No, it's not. Say that again.
No, minus 2x plus 2y. That's it, right?
Yeah, okay.
That's right.
And then what's the j term?
Negative, j. Oh, yeah. Negative 3y squared plus 2x.
Okay, there we go. Okay. Good.
And
Good.
so the vector is just
So
gonna
now,
be
wait. Akshay, what do I do next then? If to find this at 3, 2?
So wouldn't you just... Oh, at 3, 2, you plug in 3 and 2 into the...
Yeah. And the gradient is an interesting thing because it actually tells us some information. So let's actually compute this number. It is, let's see, 6 plus 4. So it's 4i is what I got. No, 10i, sorry. Adding is not my strength. Okay, and let's see. Then I got 6 minus 12, negative 6. Did I get that right?
Yeah.
Okay, thank you. I need positive feedback. Okay, so Isabel, what is the gradient telling you? Yeah, oh, sorry.
So just for three-dimensional things, like if the vector is showing you, maybe I'm wrong about what the vector is.
If you had 3 variables, if you had a function of x, y, and z, you could have a vector. The gradient would be in terms of x, y, and z.
Isn't f of x, y, like, wouldn't you graph this in R3?
You would.
Okay, so
you're getting a vector in terms of x and y, which may seem bizarre to you.
But it only has 2 components.
Right, because the surface I mean, the vector it may not be going up on the surface.
So what if, like, in 3D space, though, the gradient wasn't on the XY? Is it possible for it to not be on the XY plane?
I don't think so because of the way the gradient is defined.
Okay.
Okay. Anyway, let us continue. Charles, can you tell me something the gradient tells me?
So the gradient, kind of, I think the gradient is a vector that is tangent to both, like tangent in both the x and the y level curves of the surface.
Okay, so why is that useful information?
That tells you, so the gradient points is kind of the 3D slope of the function. It points in the direction which is steepest, and its magnitude tells you how steep it is.
So in a way, it is a kind of a proxy for what I think it's kind of a proxy for the derivative at a point in single variable calculus, because it's telling you at a point how fast the the function is changing at x and in terms of y. Let's see. So let's look back here. Eric. You were talking to me about directional derivatives. Now, what is a directional derivative?
Points in the direction of the way the function is increasing the greatest rate.
Okay, so, and the directional derivative is defined as how, Alex Johnson?
Oh, well, I was just going to say, I don't know if it's, like, it's just the rate of change of, like, some function f in the direction of some vector u.
Yeah. Okay, so we typically write it with a capital D and a little u underneath. So, but explain how I compute it, Jasper.
Well, so the directional derivative of f of x comma y is going to be the partial derivative of x comma y multiplied by the vector I plus the partial derivative of x comma y with respect to y times the vector j, and then times bracket that times the cosine of theta times the vector I plus sine of theta times vector j.
Okay, so we usually talk about it in terms of gradients, right? So how is the gradient related there?
Well, it's just the gradient times the gradient dot the u direction vector.
It's a dot product of the gradient and in a direction cosine theta comma sine theta. So that's the direction part. Okay, so let's go back to this problem. I blew it off for a second, but this is so at the point root 3, 2. Where is that point? The point root 3, 2 is like, oh my gosh, I don't know, here. Okay. Sorry,
No,
not too
right.
high. Too high. Here it is.
It's gonna be like, yeah.
Okay, so, and it says sketch the vector showing the direction of the greatest rate of increase of the function. Okay, so Alex Powell, I'm going to let you draw this time and see what you can come up with. So Alex Powell is in charge now.
All right. So I'm doing. What am I doing again? Sorry.
You're doing B. So sketch the vector showing the direction of the greatest rate of increase of the function. And this is just a level curve.
Change my name.
So you probably want to go up here, Alex, and say draw.
Oh. Okay.
Sorry.
All right. So.
Changed.
What changed?
The thing.
All right. So I'm not exactly sure how to.
Yeah, that's
how to
okay.
Find this vector.
So tell me what you're thinking about.
Is it higher in the middle or higher in the middle? I think it's fine.
So
It's okay not
I
to be
am-
sure. I mean, it really is. I mean, this is not an easy idea. I mean, it seems like we don't have enough information to figure out how to draw that vector. So ask a classmate a question. There are lots of people who can help.
Okay. So I need to phone a friend.
Okay. Let's phone Logan.
Okay, so I would think, maybe incorrectly, but I would think that you would want to do what we just did, similarly, like find the gradient.
Okay. Well, so how would you find the gradient icky here?
Okay.
Gradient icky. Do you see why the gradient is icky?
Because it's just like an ugly.
Yeah,
equation.
it's going to be hard to do. So I'm hoping I don't have to do all that work.
Yeah.
I'm hoping I don't. So maybe I do, but I'm hoping I don't. Isabel has an idea, I think. Yeah?
Well, I was just thinking, maybe this is silly, but whenever we're looking for like the greatest rate of change, we like look for a maximum or minimum of the derivative. So maybe we could do like the directional derivative and set it up so that we're solving for which like angle. I don't know, maybe I'm not making sense.
Okay.
But
That makes sense.
Huh. So, I mean, I'm hoping I don't have to do all that work for this because I've just got this pretty picture, and I'm hoping it works out nicer than that. Sam, do you have any thoughts?
Well, I just know so the dot product is 0 and the two things are perpendicular, so I'm just trying to figure out what vector would be perpendicular to the gradient at that point.
Okay. Let's see, Samya, do you have any ideas?
Yeah, I was thinking the same thing, but I don't know like how the gradient is represented on that graph.
Okay. Max, you have an idea?
So, was it?
Go
Did
ahead.
I just hear them say that they think the vector will be perpendicular to the?
I don't know. Ask them.
Did you just say that you think the vector will be perpendicular to the contour line, right?
To the gradient.
Okay, so let's go back to the hiking problem, right?
Yeah.
One of the points of the hiking problem was what, Max?
That the slope of steepest descent, the vectors would be perpendicular to the contour line.
It's always perpendicular to the contour line.
Right.
That is a fact that you must know to do this. So I don't think I have to do any work here.
And so, well, what Charles asked me, is inside the circle like going up or is it going down? And
yeah, so
I
you have
think
to figure that out.
an easy way to do that is just to pick a point or two and find f of xy and see which is greater and which is.
Okay.
Is that fair?
Yeah, so let's try it. So, like, pick a point.
So I was going to pick 1, 2.
Okay, 1, 2.
And so f of 1, 2 would be 16 over 7, I believe.
Wait.
What? Or no, 16 over 6.
Wait. Oh, wait,
So
yeah.
you're saying f of 1, 2.
Yeah, f of 1, 2.
Is 16 over.
1, 2 over 6.
Okay. And then how does that help you?
And then I was also going to pick root. I was going to find f of root 3, comma
Okay.
2.
So f of root 3, 2.
And so
That's 16 over.
10. Wait, nope. 8.
16 eighths, which is 2.
okay.
So what does that tell you?
So that tells me that inside I think the vector should be the greatest rate of increase.
So you want to draw it, Max?
Yeah,
Okay, are you Max Schroeder?
I am extra.
Okay. Okay, go for it. Logan has a question while you're doing that. Logan.
I have actually
Or you have an idea.
So
Oh, you have an idea. I love
you
ideas.
kind of made it seem simple before. So I mean, we know that this is a circle. We know that we could probably find root
How do you
3
get
2
those
on the
up?
circle,
Uh-huh.
and then because the
Get the arrows.
equation-
Where are the arrows?
That's circle, which is-
Well, so I think this is a decent approach too. What were you? Say it again,
So I'm
because
just
more
saying,
slowly.
like, if you find root 3 2,
Yeah, the point. Yeah, which is the yeah.
Can't you just draw?
I don't know how much that would be the rate.
Well,
of
you
increase.
could, but you don't know which direction that vector is pointing.
oh, you mean in or out?
Yeah, you don't know if it's pointing towards the center of the circle or if it's pointing towards the outer center of the circle. Okay, so
chance.
Is that what you wanted to do?
Yeah, I think so.
Okay, so explain what you've done, Max.
Okay. Oh.
What happened?
I thought I pressed a button.
Oh my God, Max, you're fired.
Max pressed a button.
Oh my gosh. What did I do?
It's okay. We'll be back there in a minute.
Max, you ruined Christmas.
Oh, nice.
And actually, he just failed the class too, just to be clear. Okay, here we go.
Okay.
Should woke up.
Did not press any.
I pressed that.
Stop sharing. It worked so well the first time.
Go ahead.
Okay. I think I tried to draw it perpendicular to the circle, or to the point, or the contour line, and I put it facing inwards because that's how I think the function's increasing. And then I also tried to not... We know that the magnitude of the gradient is the slope, and just judging by the 2 points we picked, it didn't slope up really steep. It went from about... just like a little under 2, or a little 2 to a little over 2. So, I wasn't going to draw an arrow that went from one side of the screen to the other.
So wait, I want to make sure. Jack, what's a takeaway from this problem, part B?
That I guess that the
Okay, Julius, can you help him out?
Well, I had a question about exactly what Max did.
Okay. Yeah, so ask Max.
So, Max, from finding the 2 points, what exactly, you just drew how did you decide that it's pointing inwards?
So, we know that f of 1, 2, which is inside the circle, is equal to 16 over 6, which is a little...
it's over.
2.
It's almost 3.
Okay, it's almost 3. And then we know f of root 3, 2, which is the point we're looking at, is equal to 2. And so I know that from the point on the circle to the point 1, 2, which is practically...
So from here to here...
It's going up.
It's getting taller.
It's getting taller.
So he just computed z values at those 2 points.
Yeah.
Are you clear on that, Julius?
Yeah, but we don't need to compare with the other side.
Well, all you care about is the direction of increase.
Because if it was negative, it was the other side.
Okay.
Right. There's no way. Yeah. Okay. Go ahead.
Yeah, I was just thinking that. Yeah. Never mind.
Okay.
When you're using this method, do you need to make sure that the points you pick have either X in common or Y in common?
No, I just think he chose a smart thing because it was, I would try to keep one of the things common because otherwise I don't know. You're kind of, if you pick this point down here, you wouldn't know a whole lot about how the function, you wouldn't know necessarily how it's changing at that point.
Pick points that are on the tangent line.
Well, I don't know. I don't know. Did you have a comment, Charles?
Yeah,
or?
I think because you know the direction of the gradient because it's perpendicular. Well, you know that the gradient's going to be in either one of 2 directions. It's going to be there and going to the left. So you can just pick something that has the same y coordinate and different x coordinates, and you'll know that that's in the direction of the gradient. So it's positive in that direction.
My concern is just that, even though this circle defines all the points on the same elevation, what's inside, some points could be,
That's
above,
true.
And some could
That's
be
why I'm
below.
saying I don't know so much about what's happening where the arrow is now. I just don't have the same. And also, the direction, the thing has to be perpendicular to the contour line. That is a fact. That was one of the facts I was hoping Jack would say as the takeaway, is that the level of steepest increase or decrease is perpendicular to the contour line. Alex Johnson, yes.
I'm just a little confused about what Izzy just said because, like, we don't know exactly what's happening in the circle and what the F values are there, but we do know that it's not going to go, like, above where the level curve is and back below because according to the intermediate value theorem, we'd have to go through c equals 2 again, and, like, that would be reflected in this level curve, right?
But this level curve in the center, I mean, let's just say that this is all we had, Alex, like this image. We didn't know the function for whatever reason. The level curves, it could have contour lines that are not circles inside, and so you can't predict how the thing is changing. Honestly, I think every level curve of this is a circle, just looking at the function and, doing my algebra 2 work. I think everything is a circle here. But, Coleman, I saw you had a question. Or a comment?
I mean, not with this function, but if this is all the information we had, couldn't, on the outside of the circle, it also increase?
Well, that's a good question.
This circle could be a valley.
You think it could be a saddle point or something like that? It could be a valley. What do you say to that, Max?
I say we could try another point outside the circle.
Yeah. I mean,
That's what I was talking about.
Coleman, I think that's a good point that you make, but I don't know that that's, given the nature of the problem, I don't think, you make a good point. So you could check the point, say, 3, 2, as opposed to root 3, 2. Alex, yeah.
But you can just also look at the function and realize that, like, as the x values get further in magnitude away from the y-axis, the denominator is going to get bigger, so the value of x is going to go down, so it's not going to happen.
Yeah, but one of the things that's kind of interesting about it is I realize now, which I hadn't really thought about, you don't really need to know the function. I mean, if you have certain data, you can still figure this out. Okay, so Jack, I'm back to you. Tell me a takeaway from this problem.
I guess that when you're taking when you have a contour line that
the direction of greatest rate of increase will be
perpendicular to it.
Yes, there we go. Okay, that's a fact. Raheem, can you give me another takeaway from this? How do you figure out which way it's pointing? Oh yeah, it does have some kind
of. With the.
Actually.
No.
So
Max. So I want to make sure everyone understood what Max did. He compared the value of the function on the rim of the contour line, and then something that was at the same y value of the contour line to show that, or was it x or y? I can't remember. To show that it was increasing in the z direction. Okay, so you have to know that's the only way you would know the direction of the pointing thing. Okay, we got to move on because we spent too much time with this problem, but I think it's a good instructive problem in lots of ways. Okay, so the gradient. Let's get some things down that the gradient tells us because this is an important thing. So, Akshay, can you tell me one thing the gradient tells us? So many things. Well, maybe I should ask for volunteers because I feel like I don't want to put anyone in the spot. Okay, Samia, help me out.
When the gradient is 0, the direction, well, that's obvious, but, have the direction of maximum increase of f is given by the gradient.
Okay, the direction of maximum increase of the function, right, is involved with the gradient. Was it given by the gradient? Is that what you would say?
Yeah.
Okay. Jasper, what about you?
Well, the direction of minimum increase of f is given by the opposite of the gradient, the negative gradient.
Yeah. The negative gradient tells you the direction of, like, steepest descent, as it were. Okay? That is going most negative. Eric.
Oh, that's not actually me, but.
Then who's? Go ahead.
I can go. Okay. Go ahead.
Yeah. Give me a factoid.
Oh, me?
Yeah.
Decrease or max?
the magnitude the magnitude of the gradient vector is proportional to the distance between the contour lines. I believe.
Yeah. So it's like the magnitude, the size of that vector tells you something about how far apart the contour lines
It's
are.
snowing.
Is it really? I love snow. Charles.
If you were to put a marble, right?
Okay, wait. This is a good one.
Wait,
This is a good one.
You
One of my
can't open
favorites.
the window, we never see snow.
Okay. It's not snowing very hard.
Oh, that's so sad.
Wait, what happened?
So, can you guys open the window? We never see
I wore a
snow.
t-shirt. Aww. It's barely snowing.
You can't see anything.
It's like snowing like this. It's not big fluffy snowflakes or anything like that.
Kind of windy.
It's really windy.
I can barely.
Yeah, no,
see
poor
it.
snowflakes. They're getting pushed around. I'm gonna trap Alex outside.
Okay, I know. Okay, Charles, you were
We
saying.
got snow in November.
Charles, you were saying.
If you were to put a marble right on the surface at a point, it would roll in the direction opposite the gradient.
Okay.
What?
So if you were to put a marble on a surface, it would roll in a direction opposite to the gradient. Why is that true, Charles?
Because it will roll in the direction of steepest decline, which is opposite the gradient.
So that's as Jasper, I think, said, that is the steepest decline. Okay, Max.
So, just to clarify, because someone said the magnitude of the gradient is like proportional to the
distance between the contour
level.
lines is what he was saying.
But isn't the magnitude of the gradient also like not proportional, but exactly the slope of the tangent, or I guess the
contour
directional
line.
Directional derivative at that point?
Now, ask your question again, because I don't think I understand it.
Isn't the magnitude of the gradient the slope
of a tangent line at that point?
Yeah, in that direction.
Let's see. Have we got all the good stuff? Charles has another factoid.
If you, going back to the marble, you could find the function that describes the marble's path by solving the system of differential equations given by the derivative of
I don't think
path
I ever said anything about that. Did I?
No, it was in the video.
Did I? Good. Okay. I'm glad to hear that. One of the things that I talk about, though, is drawing those. I assume it's in this video, how contour lines are drawn, using gradients. So go ahead and say that fact again.
So if you want to find the path that the marble will follow, it will take the path given by solving the differential equations. When you set the derivative of the marble's path is always equal to the opposite of the gradient.
So there's some ways that you can even find the path that the gradient follows, which is very cool. Okay, so the gradient is a tool that we will use until the end of this class. It turns out to be this. It's like it is one of the fundamental ideas in multivariable calculus, and it seems like it shouldn't be because it's just it's a very easy thing to compute, but it's used over and over and over again. I mean, we'll be talking about it in May still. Okay, let's see. Steepest descent and descent. Oh my gosh, let's actually. So if we have a paraboloid, and we're located at a point, and the point has suddenly shifted. Anyway, if you're located on the paraboloid at a point, in which direction would you move in order to ascend on the surface at the maximum rate, and what's the rate of change? So Sam I want to start thinking about this problem. We only have a couple minutes, but tell me what are some things you would do to compute such a question, answer such a question?
Isabel.
Are they from Florida?
That's sad.
Who's from California? Alex Powell?
Yeah. Okay.
So I would probably think about the gradient.
Okay. So I'd start with finding the gradient. So Sam, find the gradient.
So partial with respect to x is 2x plus 3y squared. Partial with respect to y.
There's no three.
I think it's your choice.
What?
It's a constant.
So Sam, what's the gradient?
Never mind. Okay, yeah. Partial with respect
What's
to
the
y
gradient?
is Okay, so it's 2xi plus 6yj.
There you go. 2xi plus 6yj. So you always have to start with a gradient here, okay? Okay, and the gradient is an easy-ish thing to compute. Okie dokie. Now, what should I do next, Alex Powell?
So after having found the gradient,
yeah,
then you'll.
So you want to move in the order to ascend on the surface at the maximum rate at a given point.
Okay, so then you would want to find in which direction. So then you'll want to. Well, then to solve that, after you find the gradient, then you would just move in the direction of the gradient.
So how? Yeah, but that's actually a harder question than I think it may be for me. At least it's a harder question. Is how do I know which direction to do? So Coleman, can you help me out? I mean, like that's an easy thing to say, but I still don't know how to get there. And you can pass.
I think if you were to test points on either side on that line, oh no, that wouldn't work.
Okay, Isabel has an idea.
Wait, don't you just find the gradient and then plug in the point?
So what if you plug and then you plug in the point, and then what would you get?
You would get the vector for direction at that point.
Okay, so if I computed, like Sam computed the gradient for a, x and y, but then if I plug in the point, x, y, I will get the maximum ascent at that point. Okay, we're going to stop. We're going to talk a little more. We are going to meet on Monday. We're going to talk a little more about gradients, and then we're going to talk about the exam, which is going to be so much fun. Rock and roll. And it's snowing not hardly here.
So like our
okay,
we're just gonna have a really rough time.
Can you not take it? What? Can you not take it? Are you kidding?
Our class is the day before.
Crap. Sure.
Oh yeah. In class.
What just happened? This is us pulling. Raise the roof.
What's up, guys?
No, teacher.
When are you coming to DC?
No. Yeah, Eric,
or whatever. Don't answer.
We wear North Face in 60-degree weather, so.
Wow, I'm so jealous.
No, it's actually warm here.
No, it's not.
Yeah, it is. It's 45 degrees.
Okay. No, it's not.
It was this morning.
It's like 60.
No, it was this morning.
Now it's like 60.
Silly weather.
Shut up, Eric.
Yes,
Eric, you were talking in the thread all class. That's so inappropriate. Just stop. It was just.
Wait, what's
Hey, Jack. Hey, Jack.
Why not wear a tank?
Oh yeah.
What just happened? What? They said, "Hey, Jack," and then nothing.
No, he said, "Why not wear a tank?" Because you rolled the sleeves up. That was so sassy of Akshay.
Kids are the sassiest people ever.